So my name is Cihangir Tezcan. I'm from Middle East Technical University, but actually Sabancı University is having a project here named encryption. So this is why I'm here today in part of this project. So my plan is to talk about some of the GPU results about symmetric cryptography algorithms. So I will talk on many algorithms in a very fast way, and I will try to summarize what we have achieved and other people achieved in the past, maybe 15 years, let's say. So, but of course, since all of these public things are published in the past, we were supported by some other projects, to most of the time by GPUs. So, the main summary of this talk is as follows. GPUs can perform parallel computation in a very fast way, especially if the algorithm is embracing the parallel. And we can use this power to obtain fast encryption, perform brute force attacks on short keys, and verify theoretical results in practice. So let me explain why these are really important. Nowadays, we almost encrypt everything, and servers are really using their CPU powers for that. And I'm going to show that a single GPU can actually use on a single SSL server to, outsource all of this encryption. Perform brute force attacks on short keys. If you Google, it is still not clear what is the key length should be in 2023. People still think that 80-bit security is enough. And I still receive papers where they use RSA-like algorithms where the group size is 1024 bits. So you have to explain to them that it is not secure in 2023. So I reject many papers just because they are saying that 80-bit security is enough, but it is not. And also, if you Google what should be the length of our passwords, they will say that 8-character passwords are secure. Again, you can use GPUs to brute force attack on this kind of stuff. Finally, what I'm more interested in, but I will probably have a short time to talk about it, many cryptanalysis results in the literature actually wrong because they are obtained in theoretical ways, and people never had to, perform experiments on the toy versions of these attacks. So when you perform an experiment on the toy version, it turns out that it doesn't work. And I will explain why this works. So, if you're not familiar with GPUs, I will actually briefly explain it without giving much into technical details. So here's a specification of one of my earliest GPUs. So I really like video games, so I really like GPUs. But at some point on, GPUs are started to be used for scientific computing. So in 2010, when I bought the laptop, which is not a gaming laptop, but like a multimedia laptop, it had a GPU called GT540M, and it has 1 GB of memory. This is the global memory. So nowadays we have more global memory, but in our GPU optimizations, we try to don't use it because reading and writing takes a lot of time. Our aim is to, do everything on the registers, shared memory, and so on. It had 96 CUDA cores, so think that this is an ordinary laptop from 2010. It is still a huge number, and it is clocked at 1.34 GHz. But of course, we shouldn't compare CPU cores with GPU cores because these cores are not that capable like Intel cores, okay? So we shouldn't confuse them. But more importantly, here the architecture is somewhat different. Actually, you cannot use different cores for different purposes. And in CPU, we can do that. If we have 4 cores, we can do whatever we want. But here, the structure is single instruction, multiple data. So if you want to perform addition, all of the cores perform addition, but they can do the operation on different data. So this way, if you have 1,000 cores, and if you want to add a matrix with 1,000 parameters, you can do it as a single clock. And GPU race actually determines how fast you can read and write. So actually in gaming, this means actually the loading time of the games. So this is why you need a larger bit here and also larger gigahertz here. One of the important things here is shared memory. Nowadays it is 64 kilobytes, and since every thread has their own registers, And instead of using the global memory, you can use the shared memory to communicate between threads. But of course, again, this is a small amount of storage, and there are some bank conflicts that I'm going to talk about when I talk about AES optimizations. But this is the fastest memory you can have on a GPU, so your aim would be to use that intensively. And also the idea is as follows. Although we have like a few hundred or 1,000 cores, generally when you write a GPU code, you create tens of thousands of threads. Think about on a CPU, when you have 8 cores, that CPU actually supports 16 threads, more than the number of cores, because you want to occupy the cores in 100%. So this way, for instance, if a thread is waiting a memory read, you can replace it with a thread that wants to perform operations. So our aim is to create thousands of threads to occupy all of these cores. And we create blocks of threads. The maximum thread number for a block can be 1024 here. And also there are limited number of registers. So this is the important part, because think about C programming. When you say that you create an integer that is 32-bit integer, so it occupies one register here. So if you can write a code where every thread uses less than or equal to 32 registers, this is the maximum occupancy you can get. So when you try to implement a hash function or block cipher, your aim should be to use less than 32 registers. So these are some of the basic ideas. But of course, high performance computing is in cryptography was also used before GPUs. If you remember, Arjen Lenstra had 215 PlayStation 3s in the past, because at that time they had 8 cores, and at that time none of the CPUs on the market had 8 cores. So he actually obtained many records in factorization or other problems. So then, of course, they have to give them freely, because in Switzerland, this only happens in Switzerland. They came and said that you have to, get rid of these PlayStations because they are now more than 10 years old. They are a threat to the, building security that may, got destroyed. So they instead gave them thousands of Swiss francs and said that buy new device. So they sent a tweet and gave more than 200 PlayStations freely to people. In Turkey, when we have this kind of situations, they say that, okay, just use the old ones. We don't care if the whole building blows up, just we don't have the money. So this is important. Okay, I just wanted to show these specs because so this 5 actually determines the generation. So years later in 2016, I guess, I bought another laptop. This one was a gaming laptop. As you can see now, I have a lot of cores, more memory, but less gigahertz now. But, memory speed is faster. And now we have more registers available per block. So here, this number actually determines your capability of your GPU. So at the 1 version, this number, for instance, was 16, which is important when you can create tens of thousands of threads, but they work in 32 of blocks. So you focus on warp. So in the first version, it was really bad, but after this point on, the specifications got better. I'm showing this because we are going to perform arithmetic operation on GPUs, because we are going to use hash functions or block ciphers, slim ciphers, and so on. But if you look at the specifications of GPUs, they will show you gigaflops per second and that kind of stuff, because they work on floating point arithmetic most of the time. But here we are going to do integer arithmetic, let's say. So I move on. I bought the Ultrabook, which is very, very small GPU. It's not even GT or GTX. But the thing is that it has still many cores and many hertz, and it is newer version. If I go back, this had this many cores at lower speed. This has lower cores but higher speed. And this Ultrabook actually works faster than this gaming laptop. In 1 or 2 years, the new devices become like 4 times or 6 times faster. So GPUs don't obey the Moore's law. This is the good thing, because you put a lot of cores as you want. So if you move on to desktop GPUs, GTX 970 is one of my favorites. It was one of the best at that time. It has close to 2,000 CUDA cores at a very nice speed. And as you can see, the memory clock rate is now increased, so the reading and writing is really fast here. So I move on. This is the best we have nowadays that you can buy on the market, RTX 4090. As you can see, it has 16,000 CUDA cores, 24 gigabytes of memory, and they are clocked at really high speed. So you can actually do a lot of stuff with this new devices, and I will show you some benchmark results in the following slides. So let me start with other people's work. So collision for SHA-1 was found. Sure, of course, whenever you want.
Can you define exactly what you mean with the CUDA core?
So a CUDA core, actually, so idea is a symbol in...
It's not the same as...
CPU cores, yeah. But in the past, they could only work on, basic matrix operations, so they were only used for gaming. But around 2006, I guess, they said that let's do it for scientific computing. So they put instructions like, basic instructions like addition, XOR, and so on. So these cores actually perform that kind of stuff. So in C programming, instead of writing for the CPU, you can write your code for GPU. And that all of the cores run all of your lines in parallel. So actually these cores are capable. They can work on 32-bit data. They allow you to work on 64-bit data, but in theory they divide it into two 32-bit parts, and so they perform more operations. So you can actually do any arithmetic operation you want, but they are not as capable as CPU cores, because for instance in Intel CPUs you have AES new instruction sets where you can perform AES encryption on the hardware. So you don't have that kind of super instructions on this core. So they only support basic operations. For instance, if you use NVIDIA cards like here, you have shift operation, but you don't have rotation operation. You have to, perform 2 shifts and then end. But in AMD cards, you have rotation operation as this instruction for the cores. So their capability changes according to this number. So most of the time you have to go to their manual and see what are the new capabilities. Okay. So Wang found a collision for SHA-1 in theory years ago, but people couldn't find it in practice because you have to perform around 2 to the 60 operations, and that is not a problem, but you have to store and check for collision. So memory was another problem. So around 2015, people found a free start collision. So Mark Stevens' team actually did what I wanted to do. So as you can see, they use 64 NVIDIA GTX 970. The idea is like this. On a single desktop, you buy a motherboard that supports 4 GPUs. You put 4 of them and buy 16 that many computers. Since search is embarrassingly parallel, all of the GPUs search the other parts, but of course you have to at some point, look at the results and see if any collision occurs. So here they made a time memory trade-off. They tried to store less but do more operations, so they performed around 2 to the 57 SHA-1 evaluation. So this is a collision, but we say that it's a free start because IVs are different. So in practice, you use the same IV. But here Mark Stevens said that this shows that if I had more GPUs, I could find a collision. Then Google said that, okay, we have a lot of GPUs, but we won't tell you how many. You will run the code on our servers and we will give you the results. So 2 years later, they finally obtained a SHA-1 collision. Here the IVs are the same, but this is 2 message block collision. The colored parts are where the differences are. As you can see, this starts with 7F, this starts with 7.3, so there's a few bit differences, but at the end you obtain the same output. So this way a long time problem is solved by GPUs. And in gambling side there were many ideas like you bet for saying that there will be a SHA-1 collision in practice before 2020 or that kind of stuff. So if you bet, maybe you earned a lot of money here. But some people also earn money from this SHA-1 collision. This is one of the best examples when I talk about blockchain. So in Bitcoin, you can transfer Bitcoins to addresses, but you can also transfer money to a hash of a script. So Peter told about the script, and that script is here actually. So these are opcodes for Bitcoin, and this checks, so you provide 2 inputs to this opcode. It first checks if they are identical. If they are not identical, it performs SHA-1 on both of them and check if it equals. So if it is equal, then the code returns true, so you can claim the money. So in 2013, he sent Bitcoin to this address, and this is actually the hash of this script. And only people who has a SHA-1 collision can withdraw this money. So they wanted to encourage people to find SHA-1 collisions. The same thing applies for RIPE-MD and SHA-256. So if you can find a collision, you can withdraw this money. So people also kept transferring money to this address. You can look at the history if you click on these links. But at the end, somebody, 3 days later of the Mark Stevens collision, they withdrew this money. But the thing is that this collision doesn't work here because this IV is not the same IV in the standards. So you have to perform a prefix attack and find a prefix that starts with the original IV that is written in the NIST standards and so on. So somebody found this collision, 5 blocks. The last 2 blocks are the same as the picture I showed you. So they added the same 3 blocks to the beginning of this so that they started with the original IV. So by just providing this input, these 2 inputs, they withdrew 2.5 Bitcoins. So it is more than, at that time, at some point, 1 Bitcoin was more than $65,000. So some people earned out of money. Of course, this was before the Bitcoin hard fork, so this account also valid for Bitcoin Cash, and the same person withdrew the Bitcoin Cash at the same day and so on. Okay, so I'm moving on. I want to talk a little bit about password security. So let's look at, for instance, VPA. In our routers, we select an SSID, then passphrase for our modem, and give this passphrase to people that visit our home. So in practice, it uses password-based key derivation function. So from your password and SSID, so your password is the input to a SHA-1 algorithm. Your SSID is the salt. So you take the hash of it, but repeat this process more than 4,000 times. And the result is your AES 256 key. So this number actually shows you how easy to perform or how hard it is. So if you're not proficient with this, for instance, when you keep passwords of users in your database at a web page, this number is generally 1. So if you can calculate fast hashing, you can actually break passwords. So instead of 4,000 times, if this number were 1, trying every 8-character password will take a few hours for you. So this is why you are making it hard. So instead of if you can break a password in 1 day by making this 4,000, now I have to do it in 4,000 days. That is the idea. And WinRAR actually did something in a better way. They use SHA-256, and instead of 4,000, they use 2 to the 15, which is 32,000 times. So question is, if I have very fast SHA-256 implementation, how long it will take for me to, capture a WinRAR password, okay? So this is a little bit old result, so we used GTX 970. We showed that if you only use numbers, but its length is 13, it takes this many years on a single GPU. If you use 6 characters, but only small and capital letters and numbers, and if the length is 6 characters, it takes 41 days. So if you go this way, we showed that if you use any 8-character password, it will take 13,000 years on a single GPU. So it might look, okay, then 8-character WinRAR passwords are secure, but nowadays we have a lot better GPUs, so you can divide this number maybe by 13, so it will take 1,000 years on a RTX 4090 or maybe less, but if you have 1,000 GPUs, it will be 1 year, right? Or if you have more, or even gamers on the internet like World of Warcraft players get together and use their GPUs to capture these kind of passwords in a few days. So 8 characters are not even secure for WinRAR, which is one of the best I have seen in practice. People use less than this number. So if it is like this for this, think about what will happen or Wi-Fi passwords. So I think 9 or 10 characters are better And here, yeah, there is a note for here. So this is SHA-256, and we use the optimizations that were used for Bitcoin mining. And nowadays, no one can mine Bitcoin with GPUs because we have ASICs. But in the past, before ASICs, we observed that AMD GPUs were better than NVIDIA GPUs when mining Bitcoin. So people try to understand why this is the case, because top NVIDIA and AMD GPUs give similar gaming performance, but when they were used for Bitcoin mining, AMD were better. There were two reasons. One of them is the architecture. NVIDIA used less cores with higher clock speeds. AMD used more cores with smaller clock speeds. So in that optimization for SHA-256, having more cores were a better choice. And another thing is that AMD GPUs have rotation instruction in their cores. So at a single instruction, you can perform rotations which are used in SHA-256. But NVIDIA, you have to perform, two shifts and the end. So this is why. So these numbers can be a lot better with AMD GPU. So this is why I wanted to say it here. Okay, so I'm moving on to some Steam Cipher results. I will pass this one, this part in a very fast way. But if you want to listen to 2G GSM communications, you can do it in real time because they are using a Steam Cipher called A51. So it is easy to capture some part of the plain text and the cipher text. So it is very easy to capture some part of the key stream when you are listening to communication. So your aim is which secret key produces this key stream, right? So you can perform a brute force attack. The secret key is 64-bit. So you need to perform 2 to the 64 encryptions to obtain this secret key. And you can do it with a few hundred GPUs. You can do it in a few days. But the thing is that you don't have the luxury to spend a few days for every communication, right? So you want to perform the operation once, store everything, and then do it in real time. But of course, we cannot store this many results. So idea is to perform time memory trade-off. So if you perform a little bit more than this many operations once, store the results in a rainbow table. For instance, nowadays it is easy to buy 8 terabyte hard drive. So create your tables as the size of 8 terabytes, put it into your hard drive, put an ARM processor on it, put an antenna, and put it into your backpack. While you are walking, you can listen to everybody in real time if you want. So it is very easy to create rainbow tables with GPUs. And of course, I said 2G, but even in Turkey, more than sometimes 50% of the communications use this algorithm. So actually, you can listen to everybody. It depends on the base station, your capability of your mobile phone. If you are calling somebody who has an old phone, then you may force to use this algorithm anyway. So next thing is my favorite Mifare Classic 1K card. So if you have an Android phone, you can check the model of your smart cards in your wallet. So Mifare Classic 1K cards can be cloned easily. So there are online attacks where you capture the card, perform 10 minutes of operation on it, like a side channel attack, give the card to the owner. Then by looking at the results, you perform like a few more minutes of operations, and then you capture the secret key. But this is an online attack. In the offline attack, you can communicate with the card in less than a second. So by moving next to somebody, you can actually, if you have the proper antenna, you can take data from the card owners from the card in their pocket. Then you need to perform some operations. So in the past, they showed that with this GPU, it will take like 10 days to get one of the secret keys from this card. So they said that it will take 14 hours if you have 16 GPUs. So I'm talking about this because if you use the reference implementation, I say that in a naive implementation, it takes this many times. But in practice, especially for the block ciphers, I will show that we can also use table-based implementation or sometimes bit-sliced implementation. In this scenario, it was easy to perform bit-sliced implementation because the registers in the stream cipher were 48 bits. So using 48 registers on the GP implementation, you can perform this brute force attack in a very fast way. So I showed that I can actually do it on a single GPU in 5 hours instead of 9 days here. So if you find the best optimization for the GPU, you can really get a lot faster speed ups here from 9 days to 5 hours. So in, today's GPUs, this takes less than an hour, like maybe 10 minutes or something. So they're also in the hardened version of the card, you have to do something more. First, you need to know one of the secret keys in the card, then you perform an attack. But they show that on this GPU, it takes like a month. So people thought that, these attacks are not that practical. And they said that if you have 180 GPUs like this, you can do it in an hour with this many costs. But the thing is that having around 200 GPUs, you have to build a huge lab with many desktop computers and so on. But instead, you can, again, perform a bitsliced implementation, and we reduced that to 7 hours too. So knowing the architecture of the GPU, you can get a lot better implementations. That is the catch here. So let me move on to AES and show you the good results. So AES is most arguably the most used encryption algorithm. And you can use the naive implementation. You can put the SBox operation, matrix multiplication, and so on. But if you perform table-based implementation, and I will show you how you did, you can actually get a lot faster speeds on GPUs. Here there's a problem which is called bank of links, because we are going to put these tables on the shared memory, and there are only 32 lanes to reach to the shared memory. But you have a lot of threads, so they will be using the same data lane, so that will be serialized, and this is called a bank of link. And I will show you how you can implement this algorithm without any bank of links. Another implementation type is the bitsliced version. So think about AES block size is 128 bits. So you can store this as 4 registers, right? 4 32 registers. So it will use 4 registers on the GPU. But if you use the bitsliced implementation, you need to use 128 registers, like for every single bit, because think of it as a horizontal, now you make it actually vertical and store every bit on a single register. So this is why you use a lot of registers, and in the beginning of the slides, I show you that there are actually limited number of registers per block. So this way, actually, you cannot occupy the GPU completely. But in the literature, one of the problems is that people published a lot of results. I will show you in the table in the next slide. But in science, an experiment should be reproducible, right? So I should be able to perform the same experiment and obtain the same results. But people don't share their source code. So we don't know if those numbers are correct, because they also use some GPUs that are not available to purchase nowadays, so we cannot verify their results because they performed these operations 10 years ago, so we don't know if they work now. We don't have those GPUs. And people always compare GPU results with CPU results, but in CPUs, we have AES-NI instruction set, right? So people generally don't compare their results with this. So in one of the latest work, we actually perform a table-based implementation by removing this bank of links in the tables, also in the SBox operation. Then we realized that there is a nice instruction in NVIDIA GPUs, which is not rotation, but which is actually byte permutation. But think about the row shift operations in AES, you are actually changing the places of the bytes. So with a single instruction, we can perform these rotations. So let me explain what the table-based implementation is. Think about the steps of AES. You have add round key here. Then you have sub-bytes, you take the 1 byte value, perform SBox operation. This row does not move, but this one is rotated 1 byte to the left. Then you perform the matrix multiplication on columns. So table-based implementation works like this. So this SBox actually can have 256 different inputs, right? So you can actually, in the SBox table, you write the output as an array. But you also know what will happen after the shift row. This doesn't move any place. But you will also multiply this with matrix, so you can actually pre-calculate the 32-bit value, okay? So this means that instead of performing all of these operations on bytes, you can actually create a table for all of the columns like this. So so assume that your input is X, a single byte. For the table of T0, this will be the output 32 bits, okay? And this one for the T1, so you need to have 4 tables because you have 4 different rows and columns. So at the end, your single AES table-based implementation works like this. So CIs are your columns. So you take 4 bytes from these columns, okay, put it into 4 different tables, XOR them, and also add your round key, 32-bit value. And this is the one column result. So you do it for all of the columns, and this is just one round of AES. This is also actually available in the AES papers. This was already suggested by Vincent Raymond and John Damon in the initial publications. But such a table, you have 256 values, and the result is 32-bit. If you multiply, this takes 1 kilobyte for a single table. Since we have 4 tables, we can put these 4 kilobytes on the shared memory, which is 64 kilobytes, so it fits in the shared memory, so we perform very fast encryption. So instead of performing every operation, a single run is like this, okay? 4 table, 4 memory accesses, XOR them and XOR with the key. So it is really fast. So the thing is that now I mentioned that there are shared memory bank conflicts because shared memory is the fastest memory type of GPUs. GPU threads are grouped into warps of 32 threads, and there are 32 data lines for the shared memory. So if every thread uses the different data line, then no conflict occurs. But we cannot know the input beforehand. So maybe 2 different threads on the same warp are going to use the same data lane. And let me show you how the data is stored in the shared memory. Assume that you create a table like I mentioned. So since there are 32 lanes, so 0th entry, 32nd entry, and so on are stored in the first data lane. So if one thread tries to read this, and the second thread in the same warp tries to read this, they need to use the same data lane. So this is what a bank conflict is. So in the past, there are many results. I will show them. All of them use this same implementation. So what I suggested is to use the following. Instead of keeping a single table, just copy the table 32 times. And this way, for instance, this value is stored in every data lanes. So each thread will use its own data lane, and they will never make a conflict because all of the 32 threads will their own data lanes, and every data is on the same data lane. But the problem here is that if you copy the table 32 times, it requires 32 kilobytes. I have 4 tables, so I need 128 kilobytes, and current architecture doesn't support it. So I cannot put all of these tables in the shared memory. So what I do is as follows. If you go back to these tables, these are Galois multiplications, by the way. As you can see, there are just byte rotations, right? So idea is keep one table, T0, and then obtain the others by just rotations. So this way you obtain a shared memory, remove the shared memory bank conflicts. In the last round, we don't have the matrix multiplications, so we have the perform SBox operation. You also put 32 copies of the SBox. You also remove the bank conflicts here. And finally, as I mentioned, instead of performing rotation as 2 shifts and an AND operation, we found this instruction from the manual of NVIDIA and used it. So let's look at the results and explain why this improvement is important. Because in the past, we have many papers from people showing that, you have a lot of, gigabits per second. So they actually perform ECB mode of operation or counter mode of operation, which are parallelizable. So you have thousands of cores. Every core encrypts different part of the block. So it is embracingly parallel. This way you can obtain really high speed. But the problem here is that, as far as I know, by the way, all of these are table-based implementation. The last one is bit-sliced implementation. And by looking at this table, you might say that, okay, for instance, from this paper to here, they obtain a huge speed up. But the thing is that this is an old GPU and this is a newer GPU. So maybe this implementation is actually worse than this one, but they have better speed just because they have better GPU, right? How do you compare this? Similarly happening here, this card is really faster than this one. And none of them provides the source code, so you cannot compare them. But again, they forget to compare the results with AES-NI instruction set, because before these instructions are announced in 2010, Intel people actually showed that on a 6-core Intel CPU, they can achieve this result. So this publication actually is worse than CPUs. But in the paper, they show, software implementations on CPUs. So they say that we have 25 times speed up and so on. So first, what I did was to look at modern CPUs. As you can see, this is the very old generation. So I looked at the 6th or 10th generation. So this one has 4 cores. This one is, I think, 8 cores. So as you can see, the speed is somewhat proportional with the core numbers. But again, most of the results are no longer competing with the CPU results, right? When I use our shared memory bank of links, when I remove them, I obtain that on a GTX 970, I can achieve this. So if you look at the past, people had this. So it is like close to 3 times speed up when you remove the bank of links. So you just copy one table 32 times just because you know the architecture of the GPU. So you obtain this speed. So in a better GPU, I obtain this one. So again, this is not a fair comparison, right? Maybe this GPU is a lot faster than this one. Maybe it has a lot more cores, right? So what I suggested to look at the TDP, which is the maximum amount of energy they consume when you fully occupy the GPU or CPU. So if you look at the CPUs, they actually consume less power than GPUs, right? So this is why this CPU result, when you look at gigabits per second per watt, is really high, so a lot better than the previous publications. So this one is our latest result on this GPU, so it's like 2 times faster than the CPU. So long story short, you can actually put a GPU on a TLS server and outsource all of your encryption and decryption on this GPU. And this way you can reserve your CPU cores for other operations. But as you can see, these are really huge speeds, and this is also 2-generation old GPU. Before coming here, I also performed operations on our newest GPU. So the thing is that I also put the source code, so if you obtain better results, just compare it with the source code. So as you can see, here if you use the very small GPU on my Ultrabook and use AES-256, you still get 60 gigabits per second. So think about this, most of the SSDs don't have this many write and read speeds, so it is faster than your hard drive anyway, so you can obtain really good results. But more importantly, just before coming here, since I recently get this GPU, I just wanted to check its performance, so I can actually encrypt more than 4 gigabytes, not gigabits, 4 gigabytes in a second. So it's really, really huge number. So if you have a few terabytes of hard drive, you can actually encrypt and decrypt it in a few seconds. So this is the thing. But of course, you need to have a device that has that write speed and read speed. Okay. Similarly, I use this device for exhaustive search. So I wanted to check if I perform an exhaustive search, how many keys I can try. In our recent GPU, I observed that I can try more than 2 to the 35 keys in a second. So this is important because, we are not going to break AES by performing a brute force attack, but most of the time we may need to perform experiments on smaller part of the key in cryptanalysis, so these results help us a lot. Actually, we obtain collisions for AES when you use AES in the hashing mode like Devious Mayer and so on, and we use these implementations to obtain the collision in a few seconds. Yes, these are the results. Let me just briefly mention this. When we looked at the Copan or Riviera like FPGA-based clusters, our performance cost ratio also faster than those devices. Okay, I will finish the block cipher parts with an example from Present. So we implemented Present in the past, have a table-based optimization, but this one is slower than AES because Present has 31 rounds. So AES have 10 rounds. So you do everything in a for loop for the number of rounds. So having more rounds actually means slower speed in a table-based implementation. But I want to show this figure because This is one of the first things I use GPUs. I think the result from 2014 or something. So in a Tesla GPU, I obtained this result. But I mentioned shared memory, right? It stores 32-bit registers. But in the past, there was an instruction saying that, okay, just enlarge these shared bank memory parts to 64 bits. So just putting one line of code, the same GPU actually achieved this many encryptions. So, but they removed this instruction after those generations, so it does no longer work. So you have to be very familiar with your GPU and its capabilities. So NVIDIA thought that nobody's using it, so they removed it. But actually, in very special cases like this, it actually allowed us. Because in present, the block size is 64-bit, and I created tables which are size of 64 bits. That was the thing. So this is why you have to know your architecture. So on a new GPU, we actually optimize this, and we realize that we can search many keys in a second. I want to show this because since present supports 80-bit secret keys, if you have millions of GPUs, you can actually perform a brute force attack in a year. Again, this is an old GPU with RTX 4090. Probably you will reduce this number to a few millions. And there are many gamers using these GPUs. So you can actually, get together with GPU owners and, capture 80-bit secret keys just by GPUs if you want. So with a dedicated device, you can do this in a faster way. So I will conclude with some cryptanalysis results. I really encourage people to perform their cryptanalysis results. I mean, they should verify their theoretical results on the toy versions of these attacks. So I want to show an old example from 2008 when Dunkelman et al. Tried to break Serpent by performing differential linear cryptanalysis. So they found a 9-round differential linear distinguisher. But the thing is that, you use a few rounds of differential, a few rounds of linear distinguisher, and you try to combine them. And, you have probability for the differential and bias for the linear approximation. So let's say the differential has probability P, and in the other one, the bias is Q. So you have like P squared times Q many probability here, theoretical bias. So they performed an operation to see how this 3-round differential matches with the 1-round linear distinguisher. So they performed 4-round experiments and showed that this bias is actually this in practice. Actually, in the paper, they say 75. But I use more data, so I think that my precision is better. But think about it again, in 2008, they had only CPUs. So they could perform a small number of experiments, and they showed that this actually this. And they used this number in the paper. So question is, if they had more power, and if they checked 5 rounds of that distinguisher, would this gain still be there? Or would be better or worse? So since I have GPUs, I performed this experiment with many data. So in the 5-round, the theoretical bias is this, and in practice, it is this. So you obtain a little bit more gain here, as you can see. So since I have more power now, I use 6 round, and again, I obtain a little bit gain. So this actually means the following. In theory, we find the distinguisher and use it, but in practice, maybe there are other paths starting with the same input difference, going some other place, but coming back. So you have actually multiple differentials, and it is not easy to check everything. But with the experiment, you actually see it in practice. So what I suggest is that in practice, for instance, if you find a 10-round distinguisher, probably you cannot verify it because probably you will need to perform the operation with 2 to the 120 many pairs. But instead, reduce it and check the practical bias or probability there, and then, add the remaining part to it so that you obtain better results. So in practice, most of the attacks actually works better, but sometimes, some attacks never work in practice because they actually do it in theoretical ways, say, and write things like, okay, guess this part of the round key, perform partial encryptions, and then obtain the secret key. But in practice, sometimes S-boxes have some properties. For instance, in a differential cryptanalysis, you want to see the correct key with the highest counter, right? You perform the operation many times and see if the distinguisher holds. But in practice, when you perform that attack, you will see that more than one key gets the same counter every time, because due to an S-box property, they are somehow related. So again, most of the theoretical attacks don't work in practice, and sometimes most theoretical attacks works better in practice, so you have to perform this kind of operations. So let me also finish it by a more recent result. So for ASCON, we observed, again, a different situation. So there was a 4-round distinguisher like this. So here, so ASCON has 320 internal states, so each row is 64 bits. So here we actually giving a difference here to the nose, I guess. Then, you look at what happens after the S-box. Due to S-box, there is no difference here. That, unknown values, question marks, are scattered around due to here the permutation operation is just adding the row to itself by permuting it a few many times. Then you perform the S-box operation and so on. Then you put an linear approximation. Here the notation is different. These are hexadecimal. So idea is to have 0 or 1 differences to the masked bits in your linear approximation. So this means that if you follow the differential in pairs, there are no differences at these 0 positions. And if you mask those positions, after 2 rounds, you look at this mask. So in a differential linear attack, you give the difference and check this XOR of these bits. Okay, that is the idea. And why I'm talking about this, the reason is that this 4-round distinguisher has a theoretical bias of 2 to the minus 15. But the thing is that in practice it is 2 to the minus 2. So there's a very huge gap. And people try to explain it with different methods. They say that let's introduce something like differential linear connectivity table. So Baran et al. Actually showed that due to some paths, this is actually 2 to the minus 5. But again, in practice, it is even better than that. So my explanation to this is, since the internal state is really huge and we are looking at a small number of rounds, the confusion and diffusion properties of the cipher is not good enough in 2 rounds. This is why, when you give a difference, actually you don't see any difference on this, most of these question marks. This is why it maps to this part in a higher probability. So this is why you need to perform experiments. And we also observed something. So in the NIST competition, there was another algorithm very similar to ASCON, but called drag ASCON. So we found a distinguisher for it too. So I think it was 5-round distinguisher, 2 rounds of differential, 3 rounds of linear approximation. And this has bias 2 to the minus 7.98 in practice. So we obtained this theoretically so that no question marks are mapped to these input masks. But the thing is that since this theory and practice has a very huge difference, because this also in theory I think the bias would be 2 to the minus 20 or more, but in practice we have something a lot better. We said that, okay, since we cannot actually follow all of these paths and these question marks are most of the time are not correct, instead of trying to find such a distinguisher, let's perform experiments on distinguishers we actually don't obtain by theoretically. This means that, for instance, here you are giving a difference to one S-box. Here, if you just give this one instead of this one, all of the question marks are shifted. So here, one example is this. We give the difference here. So we have question marks here. And we use the same linear approximation. But the problem is that now some of the question marks actually coincide with this masked bits. So in theory, this is not a distinguisher. So I cannot actually write the paper saying that this is a distinguisher because it is not. But the thing is that if you perform an experiment, it works with better bias than this one. So in practice, it works. So I found a distinguisher experimentally that I cannot obtain in theoretically. So my suggestion is to, when you have 2 different cryptanalysis techniques and if you want to combine them, just perform an experiment if it really works and if it is better than what you obtain theoretically. So we performed the same thing for ASCON. so I don't have any slides left, but next week at the NIST workshop I will try to explain. So we obtain some related key attacks or distinguishers for 5 rounds. We obtain them experimentally, and those results are better than the ones we obtain theoretically. So I think that will be all. So I put all these GPU codes to GitHub. If you're interested, you can find them there. And if you have any questions, I will be happy to answer. Thank you for your attention.